Hi guys, my name is Shay and I'm a second year biochemistry major from the class of 2020. I'm going to show you how to work through question 14 from section 5.3 skill builder problems. This is a calorimetry problem with a twist. If you haven't had a chance to try this problem first, pause the video here and see if you can get the answer by yourself, and then watch to see if you did it right. The question tells us that we have 100 grams of ice, initially at negative 5 degrees Celsius, and it's added to 100 grams of hot water, initially at 90 degrees Celsius, in a styrofoam cup. The question tells us that the cup insulates the contents from the surroundings, so we can assume that no heat is lost. The question asks us to find the final temperature of the contents once thermal equilibrium is established. First, we need to figure out what we know. Let's talk about the ice first. We know that we have 100 grams of ice at negative 5 degrees, and we know that that ice is going to heat up before it melts. So there's going to be an energy Q associated with that. We can write this as Q1 of ice warming. We also know that the ice is going to go through a phase change at 0 degrees, so we have a Q for ice melting. We're going to call that Q2 of ice melting. After the ice goes through a phase change, all of the water that used to be ice is going to need to warm up from 0 degrees to whatever the final temperature is going to be. We're going to call this Q3 ice water warming. The sum of all three of these expressions is going to be the total energy, or the Q for the ice. So that's what we know about the ice. Now let's talk about the water. We know that we have 100 grams of water at 90 degrees, and when we put ice in it, the water is going to cool down to some temperature of equilibrium. We can call this Q of water. Now we can start defining Q. Let's start with the Q of the ice. The first thing the ice is going to do when introduced to the water is rise in temperature from negative 5 to 0, where it will melt. We need to write an equation for the energy needed to raise the temperature of the ice. Be careful though, because the ice is not melting at negative 5 degrees. It needs to heat up to 0 before it can undergo a phase change. We're going to use the equation Q equals mc delta T to express the ice warming up. We're given the mass in the problem, 100 grams, so that's going to be our M. And our change in temperature is from negative 5 to 0. We're going to write it as finest minus initial, so 0 minus negative 5. Finally, we need the specific heat. We can't use the specific heat of water because that would be water in its liquid state. We need to look at our equation sheet and we see that the specific heat for ice is 2.108 joules per gram Celsius. We need to do a quick conversion from joules to kilojoules, so we actually get 0.02108 kilojoules per gram Celsius. So we input those numbers and we get 10.54 kilojoules, and that is the energy associated with the ice warming up. Now we need to write an equation for the ice changing phase and melting. We're going to use Q equals N delta H, where N is moles and delta H is the heat fusion of water. We get moles from dividing the mass of ice, 100 grams, by the molar mass, 18 grams per mole. Next, we go back to our equation sheet where we find the heat of fusion of water. It is 6.01 kilojoules per mole. So we can input all these numbers and we get 33.39 kilojoules, and that is the energy associated with the ice melting. Finally, we need to warm the ice up to its equilibrium temperature that we don't yet know. So let's write an equation that we do know. We're going to use the same equation, Q equals mc delta T. So for Q3, we know that the mass is 100 grams. And we know from our equation sheet that the specific heat of water is 4.184 joules per gram Celsius. Again, we need to convert this to kilojoules, so we get 0.04184 kilojoules per gram Celsius. Now we have an unknown variable. We know that the starting temperature of water is 0, but we don't know the final. So we can write this as final minus 0, which is the initial, for delta T. When we plug all these numbers in, we get 4.18 times the final temperature. Now that we have all three stages of the ice figured out, let's talk about the water. This one should be pretty simple. We have 100 grams of water that starts at 90 degrees and ends at some final temperature. We're going to use the same equation, Q equals mc delta T. So the Q for water is going to be equal to the mass, which we know is 100 grams. C is going to be the specific heat for water, but remember we have to change it to kilojoules because everything else in our equation is in kilojoules. So the specific heat is 0.04184 kilojoules per gram Celsius. Now we have to write delta T in terms of our variable. Remember, we always write finest minus initial, so our final temperature minus our initial temperature of 90 is going to be our expression for delta T. We can plug these in and we get 4.18 times that final temperature minus 376.2. So we also know that Q ice is going to be equal to negative Q of the water. Why is Q water negative? Well, the water system is losing heat. So anytime a system loses heat, we put a negative sign because the system is losing that energy. Now we can add all these parts together. The sum of the Q for the ice system is equal to the negative sum of Q for the water system. So we have 10.54 kilojoules plus 33.39 kilojoules plus 4.18 times that final temperature, and that is all going to be equal to the negative of this. So we have negative 4.18 times final temperature plus 376.2. So now we're going to do some algebra to put our variables on the same side. We can subtract 33.39 and 10.54 from this side, and we can add 4.18 times the final temperature on this side. So we get 8.36 times that final temperature is equal to 332.27. Divide each side by 8.36, and we get that the final temperature is 39.7 degrees Celsius. Thanks for watching, and I hope you guys master calorimetry.